I'd like us to look at the Haber process. Our learning objective for the Haber process will cover meaning of the Haber process, what the Haber process actually means, what it's about, sources of the reagents used in the Haber process, the challenges faced in the process, important conditions that are associated with the process, there are things to note, and then review questions. The Haber process is a term that describes the industrial manufacture of ammonia. Ammonia, we know, is a covalent compound and is NH3. Ammonia is NH3. In ammonia, nitrogen covalently bonds with 3 atoms of hydrogen. Now, the industrial manufacture of ammonia is what we call the Haber process. We're not going to look at a structure this big for producing ammonia. We're looking at a structure smaller as we'll see later. But then, let me tell you a few things about ammonia. Ammonia contains an atom of nitrogen, 3 atoms of hydrogen. It is very useful, especially for making fertilizers. It is very useful for making fertilizers. Ammonia usually can be a gas, it can be liquid, but normally aqueous ammonia is a liquid. You will see a lot of aqueous ammonia being used in your paper 6 in qualitative analysis or salt test. That process is going to be simplified into 3 simple processes or into 4 simple stages. In the production of ammonia, we react nitrogen and hydrogen to form ammonia, and to balance the equation, I believe, I'll put a 2 here and put a 3 here. The nitrogen made is a gas, or nitrogen or used is a gas. Hydrogen used is a gas. The ammonia made is gaseous, but it will be condensed to become a liquid. First of all, nitrogen is sucked into a chamber. Hydrogen is sucked also from these 2 points. From there, both gases mix and are sent to a reaction chamber, where certain conditions force them to react, and the ammonia made is condensed and stored in a tank, ready for distribution or for use to industries and individuals that need ammonia. I repeat, nitrogen and hydrogen are fed into this chamber. The gases mix here and are sent to this reaction chamber. This is like a collection, while this is a reaction chamber. Certain conditions force them to react. The ammonia that comes out of the reaction sent to a condenser, where it cools down, becomes liquid, stored in a storage tank, a reserve tank, and then it is sent for distribution. I'll take the steps one by one. Nitrogen. How do we get nitrogen? Nitrogen is obtained from fractional distillation of liquid air. Nitrogen is obtained from fractional distillation of liquid air. Hydrogen, on the other hand, is obtained from cracking hydrocarbons. So this is from fractional distillation of air, while this is from cracking hydrocarbons. These are the sources of nitrogen and hydrogen. That is like a collection chamber. Now next, it is sent from this collection chamber to this reaction chamber. What happens in the reaction chamber is very, very important. In fact, most IGCSE questions about the Haber process is about what happens in the reaction chamber. The first thing is, at the reaction chamber, ion catalyst or finely divided ion is used to catalyze the reaction. You know what a catalyst is? A catalyst is a substance that speeds up a reaction without taking part in the reaction. We say catalyst is a substance that speeds up reaction without getting changed after the reaction. That's what a catalyst is. I believe we already know that. So I'm not saying anything new. So the catalyst in this reaction is ion catalyst. Another condition that happens in the reaction chamber is a temperature of about 450 degrees Celsius is used to cause that reaction to happen, and a pressure of about 200 atm. atm means atmospheric pressure. These are the conditions for the reaction. So you want to actually bear in mind that the temperature for the Haber process is 450 degrees Celsius, the pressure is 200 atm, and then ion catalyst. Now, the third thing is, after this, the ammonia, that reaction that happens, the reaction we talked about, now forms ammonia. The ammonia, this is balanced. The ammonia is now sent to a condenser where it becomes ammonia as a liquid. From the condenser actually turns it turns the ammonia gas to liquid. So it condenses it to a liquid, and lastly, this is sent to a storage where it is sent for distribution. So the Haber process is actually very simple. Important thing, what are the sources of the reagents? The reagents and nitrogen, we said, is obtained from fractional distillation of liquid air. You may refer to my video on fractional distillation of liquid air. And then hydrogen is obtained from cracked hydrocarbons. When you crack a hydrocarbon, you can get nitrogen. I'm not saying other sources of nitrogen do not exist, because even electrolysis of certain compounds can produce hydrogen at the positive, also at the negative electrode, at the cathode. But then I'm talking about how we get them in large amounts, for industrial amounts, is by cracking hydrocarbons. Then what about the challenges faced by in the Haber process? The Haber process has a challenge. And what is the challenge? Please, the reaction between nitrogen and hydrogen, even though we write it directly for elementary classes, it is actually a reversible reaction. A reversible reaction is a reaction that can proceed in both forward and backward direction. What it means is that this reaction, reactants can form products, and products can reconvert back to form reactants. So the challenge first in this industry where Haber process is used to make ammonia is that when the ammonia is made to a particular amount, it begins to reconvert back to the reactant, and that's not a good thing because we want ammonia. How come the ammonia is now going back to forming nitrogen and hydrogen? It is because of the reversible nature of the reaction. So the challenge here is ammonia reconverts back to nitrogen and hydrogen after a while. This is because the reaction is reversible. This is because the reaction is reversible. So this poses a problem. Can industry solve this problem? Yes. How did they solve this problem? They solve this problem by removing the ammonia each time a little amount is formed. They just remove it. So the solution is keep removing ammonia each time an amount forms. Each time an amount forms, you keep removing the ammonia. This will allow, or this will prevent ammonia from reconverting back to nitrogen and hydrogen. So the problem is the fact that the reaction is reversible, meaning after a while, the ammonia form will begin to reconvert or transform or change back to the reagent or reactant, which is not good. And the solution, keep removing the ammonia each time it is formed. And then important conditions like we saw in the process, important conditions, we said first of all, the temperature is 450 degrees Celsius. The pressure is 200 atmospheric pressure. And then we have the catalyst is ion catalyst. These are the conditions in the Haber process. Now, what about important notes? What about important notes? There are notes we have to take care of, and those are, I already told you why the process is challenging. I told you the conditions. Now, we must understand Le Chatelier's principle. If you've done Le Chatelier's principle, you can refer to my video on Le Chatelier's principle. You will see that this principle actually talks about reversible reactions and shifting equilibrium. So what happens is that this reaction is exothermic and the reverse must be endothermic. Increasing pressure favors the path with the least number of moles or least number of gaseous moles. All of these things are gases, but the least number of gaseous moles is this side with 2 moles of nitrogen. So this is the least number of gases. So increasing the pressure will favor this reaction. It will push equilibrium this way. Increasing temperature will favor endothermic, and so on. So you may want to refer to the video on Le Chatelier's principle, but for now, you must know that increasing pressure of the reaction favors the formation of ammonia. It favors the yield of ammonia. So if increasing pressure favors the yield of ammonia, and we have a pressure of 200 atm, why can't we use more pressure? Why can't you use even 5,000 atm? It's important to know that, see, this pressure is reasonable. If you're going to use pressure too much, it is expensive to generate pressure. Number one, the pressure will be too much or could be too much that it can actually rupture the pipes. So you want to stay at 200 atm, even though an increasing pressure favors the formation of more ammonia. So that's also a point to note. Although increasing pressure favors ammonia yield. 200 atm is reasonable so as not to have too much pressure that will break pipes. Also, too much pressure is expensive to generate industrially. This is an important note. Also, too much pressure is expensive to generate industrially. So 200 atm would be a reasonable pressure. 200 atm would be a reasonable pressure. Let's not forget, I am actually basing all of this on the principle by Le Chatelain. The principle by Le Chatelain. Sorry. Now, this is a gas. I said, sorry, I canceled this before now. Now, this is exo and this is endo. Good. Now, another thing is we've looked at pressure, that increasing pressure favors the yield of ammonia, or that means it favors the part with the least number of moles. It favors the part with the least number of gaseous moles. According to Le Chatelain's principle, Le Chatelain's principle is discussed in my video on reversible reactions, okay? But because increasing pressure favors ammonia formation does not mean we will have to put the whole pressure in the world. Why? The whole pressure in the world will cause rupture of the pipes and it will be difficult or expensive to generate. Now, according to Le Chatelain's principle, increasing temperature favors the endothermic reaction. It shifts equilibrium to the left. So it's going to favor the formation of nitrogen and hydrogen. So it means if we want to more ammonia, we have to cool it down. We have to decrease temperature. So I'm going to write it down also. Decreasing temperature favors yield of ammonia. Yes, but if that is the case, why then are we using 100? Why then are we using 200? Why can't we use something lower than, why then are we using 450 degrees Celsius? Why can't we use something lower than 450, since decreasing pressure is supposed to favor the yield of ammonia? 450 is a compromised temperature. If we use temperature lower than 450, the reaction will be too slow. So even though lower temperature will favor ammonia yield, too low temperature will make the reaction slow. And that is why 450 is reasonable in the process. That is why 450 is reasonable in the process. So we use 450 to increase the rate. We use 450 degrees Celsius so as to increase reaction rate, so that the reaction is not too slow. This is another important point to note from the Haber process. These are often questions they'll ask you in your IGCSE exams. These are questions 450 degrees Celsius. These are questions they could or they often ask in the exams. So these are important things to note about the reaction. Now let's see a few questions. Now, the first question here says, the question is about nitrogen and compounds of nitrogen. Ammonia is manufactured by the reaction of nitrogen and hydrogen in the Haber process. The equation, like we saw, states the source of nitrogen for the Haber process. We already done that. The source of nitrogen will be what? From fractional distillation. Fractional distillation of liquid air. It will be gotten or obtained from the fractional distillation of liquid air. The next question here says, state the source of hydrogen for the Haber process. It will be obtained from cracking hydrocarbons. State the typical condition used in the Haber process. Temperature 450 degrees Celsius, pressure 280. Name the catalyst used. You see, it's quite easy. Ion catalyst is used. State what is meant by the term catalyst. We already seen that a substance that speeds up reaction rate and remain unchanged after the reaction. Next question. Ammonia is converted into nitric acid according to the first stage in the conversion of ammonia into nitric acid. Into nitrogen is the conversion of ammonia into nitrogen monoxide. Look at the equation. The reaction is carried out at 900 degrees Celsius and pressure of 7 atm. The forward reaction is exothermic. What it means is that this forward reaction, if it's exo, then the backward reaction must be endothermic. Explain why a temperature less than 900 degrees is not used. Why can we not use a temperature less than 900 degrees? Now, what do we want to make? We want to make nitrogen monoxide. Nitrogen monoxide does not have to be made with high temperature because the forward reaction that makes it is exothermic. It means at lower temperature, more nitrogen monoxide is formed. But explain why the temperature less than 900 is not used. Now, if we say because it's exothermic, let's use a very low temperature. Let's use 2 degrees Celsius. After all, 2 degrees Celsius is cold enough and it will favor the forward reaction, exothermic. Why can't we use 2? If you use 2, the reaction will be too slow. So the reason is the reaction will be too slow at temperature lower than 900 degrees Celsius. So that's the answer. Explain why a pressure greater than 7 atm is not used. You see, increasing pressure is supposed to favor the formation of okay, we have 5 and 4. We have this. Increasing pressure will favor this actually. But if the question is asking why a pressure greater than 7 atm is not used, it is because high pressure breaks pipes and is expensive to generate. High pressure breaks pipes and it is expensive to generate. We already saw that. Ammonia is a base which forms a weakly alkaline solution when dissolved in water. Define a base. You know what a base is? In IGCSE, a base is a proton acceptor. A substance that accepts protons is what a base is. A substance that accepts protons, and an acid is a substance that donates protons. What is the pH of ammonia? Ammonia is a weak base, so I'm going to give it a pH that is not too alkaline, but is alkaline enough. I'm going to put 10 or 11 as the pH. Now, 11 means it's alkaline, but it's not too alkaline, because for very alkaline substances, we're looking at 13 and 14. Neutral is 7. So between 7 and 12 should be okay for a weak base. We'll move on to the next question. Ammonia is made in an industrial process starting with nitrogen. The equation for the reaction is shown. Name the industrial process used to make ammonia. We already said that is the Haber process. Next question. State the raw material from which nitrogen, I think I'm tired of that. The raw material is air. What is meant by this symbol is supposed to mean reversible reaction. That's what that symbol means, that the reaction is reversible. State the temperature and pressure. I think we're tired of this now. 450 degrees Celsius and 200 atm. So I'm going to put it right here. Name the catalyst, iron, sand. We're all used to that. Now you see how easy it is to answer questions involving the Haber process. Now the forward reaction is exothermic. What it means is that this is exo. It's almost the same thing we have done. It therefore means that the backward is endo. Exothermic reactions don't like heat. So when you cool them, it will favor this direction. When you cooling favors this direction, but heating favors the opposite direction. So when you heat it up, more nitrogen and hydrogen are made, but when you cool it down, more ammonia is made, and the industry wants to make more ammonia. So they're supposed to operate at low temperature. But why are they not operating at that? We've settled that question. State the effect, if any, on the position of equilibrium when the following changes are made. When temperature is reduced, what happens? It will favor the forward direction. It will increase the yield of ammonia. So go favors forward reaction. Equilibrium shifts to the right. It shifts right and it favors yield of ammonia. It favors yield of ammonia. So these are the things that are obtainable when we decrease the temperature. It will favor the yield of ammonia. Equilibrium will shift to the right and it will favor the forward reaction. What about when pressure is decreased? We already said it before now that pressure, increasing pressure favors the part with the least number of gaseous moles. If all these things are gases, so we have 1 plus 3. 1 is the coefficient, 3 is the coefficient. So we have 4 gas moles here, and we have just 2 gas moles here. So it will favor the 2 gas moles. So increasing pressure favors the ammonia production. So when pressure is reduced, it will favor nitrogen and hydrogen production. So what happens? It favors backward reaction. Equilibrium shifts left, and then yield of ammonia, can you guess? Does it increase or decrease? It will decrease since it's shifting left, but yield of nitrogen and hydrogen would increase. So those are the effects of reducing pressure. These are the effects of reducing pressure. We'll move to the next question. Oh, that's all for now. Thank you for your time. I hope you understood it. So far, we have actually looked at the meaning of the Haber process. We looked at sources of the reagents, talking about nitrogen and hydrogen, where they are obtained from. We looked at the challenges faced, that it's a reversible reaction. So the ammonia, when it forms after some time, it begins to reconvert back to the reactants. And the best way to do that, or to take care of that, is by removing the ammonia each time it is formed. Important conditions: 450 degrees Celsius, 200 atm ion catalyst, and then we've seen review questions. Thank you for listening. I'll see you around.